Welcome back to episode 15 of the Quantum Science Seminar. Today's going to be all about dynamical phase transitions, yet another topic different from what we've heard before. Please ask questions. If you have questions, please send them to us via email to quantumscienceseminar@gmail.com or use the YouTube live chat at the right or at the bottom of the screen here. As usual, we're going to take a break somewhere halfway through the talk where we can start answering some of your questions and answer the remaining questions you have at the end of the talk. Our speaker today, again, has very kindly agreed that if there are more questions than we have time for, she will answer them in written form that we will put on our webpage later, so don't worry. Also, please note that there's a 30-second time delay between what you're seeing on YouTube and what we're doing. And please take that into account. And with this, I'd like to hand over to Andrew, who will introduce our speaker today.
So, good afternoon, everyone. It's a great pleasure to welcome our speaker this week, Maria Rey. Maria is originally from Colombia, where she studied in Bogota before moving to Maryland for her PhD. And she was a postdoc then at NIST and at ITAMP before taking up her current position at JILA in Boulder, Colorado. Maria is very well known across different areas of quantum optics and atomic physics for her theoretical work that spans sort of various things from atomic clocks to the implementation and applications of many-body physics in these sorts of systems. And she's pioneered a lot of new directions in experiments through her theoretical work, particularly, as I say, in atomic clocks and quantum simulators. Maria has received numerous awards for her work, including a MacArthur Fellowship in 2013, and last year a Blavatnik Award for Young Scientists. Maria, it's a real pleasure to have you here at the Quantum Science Seminar, and we're very much looking forward to your talk.
Andrew, thank you very much for the kind introduction. It's a great honor for me to speak at the Quantum Seminar. Thank you very much for the invitation. It's going to be also a learning experience for me to give this type of online talks. I hope I can use this time to tell you about dynamical phase transitions. That is a topic that has caught my attention for the last couple months. I hope that with this talk I can convey why I think they are so exciting, and also try to tell you how powerful experiments are becoming and enabling us to actually probe the complex dynamics of many body systems. So I want to start my talk by showing, let's see, and now hopefully I can, now it was working before and now I cannot, okay, perfect. Now, the first slide, I try to show a picture of many body systems, and when you stare at them, you all agree that definitely they're fascinating and complex, from a ferrofluid, from a binary star, including the brain itself. So these type of systems are very useful, many body. And the important point that you realize is that typically they are out of equilibrium as many of the systems that we interact with everyday life. So they are very fascinating, but the issue that we face is that they're extremely complex. There are, a way to summarize their complexity comes from a famous quote by Phil Anderson, who said, "The behavior of a piece of matter is not just a sum of the behavior of its constituent particles." So basically what we are trying to say is that, or he was trying to say is that even if I am able to understand the behavior of a few particles, this is not enough to actually predict the emergent behavior that can happen in a many-body system. And well, this actually is even more complicated in quantum systems, that especially when they are out of equilibrium. The problem is that they tend to be strongly correlated and entangled. And more importantly, we lack this description in terms of statistical mechanics that has shown to be very powerful and useful for describing equilibrium systems. So we have recently, for example, discovered that out of equilibrium systems can feature exotic behaviors that actually even forbid to exist in equilibrium conditions. So we think that the time is just right to try to decode and discover these organizing principles that are behind out of equilibrium systems. And one of the questions is, if, of course, if we want to understand them and predict their behavior. And our vision is try to use very controllable atomic systems to bridge the gap between the few and the many body via quantum control. So we want to take advantage of these fully controllable atomic systems, harness them, trying to shed light onto non-equilibrium systems for applications ranging from metrology and quantum information, for example. And there are a few appeals that I want to emphasize of these systems. That is that one important component is that they allow us to understand very well the underlying microscopic Hamiltonian that describe the dynamics. So we can write the Hamiltonian in a piece of paper, and generally it can be very, very quick, very short Hamiltonian, not necessarily solvable, but very well can be captured very well in a clean manner. And moreover, we're able to tune the parameters of the Hamiltonian almost in real time and access the quantum dynamics without the need, for example, of ultra-fast probes that are one of the complications that we have in solid state systems. Well, these are very appealing, but moreover, if you look at this system, they also offer a gamut of different type of interactions that we can explore, not only to contrast different behaviors and compare between them, but also to access a broad range of parameter regimes. So what I'm showing here, for example, is that if you look at neutral gases, they are composed of atoms that, in order to interact, they have to collide with each other. They have bumped into each other. And in this talk is going to be these hockey players that need contact for interactions. So we go from here to systems that can interact at longer distance, featuring, for example, van der Waals of dipolar interactions. This is the case of Rydberg atoms and ultra-cold polar molecules. And you had in prior quantum seminars, beautiful talks about the progress into these different systems. And these go until the extreme limit of atoms in cavities in which they can interact independent of the distance. So the interactions are completely long range. An atom can talk with any other atom at any place in the array. And in this case, we have instead what I call my baseball players, because the interactions actually mediated by bosons in the case of photons or phonons, for example, depends if you have atoms or ions, and this can mediate and go over very long distance. So in this talk, I'm going to cover these two extremes. But more importantly, and this is one of at the heart of my talk that I find honestly fascinating, is that I'm going to show you that even though they look very different, actually there are parameter regimes when interacting systems with contact interactions can actually emulate the physics of long-range interacting systems. So I'm going to explain this a little bit later, but this is one of the key aspects that I want to convey in this talk. All right. So let's now start with dynamical phase transitions, but for that, let me back up and talk about equilibrium phase transitions that most likely you are familiar with. Phase transitions in generally are characterized by an abrupt, non-analytic change of behavior as a result of the change of system parameters. For example, in classical transitions, we change the temperature. And if we go to the quantum regime, where we are talking about quantum phase transitions, is another control parameter because we are setting the system at 0 temperature. So these equilibrium phase transitions are typically described by what we call an order parameter, that is exactly the quantity that changed non-analytically at the transition point. So let me, for example, show you the typical phase diagram of water, that as a function of pressure and temperature, where you see ice, water, and vapor, you can identify well the phase diagram, and in this case, the order parameter is just the density. So clearly, when you want to compute this phase diagram, what you do is by the minimization of free energy, and the way that you look at explore the different quantum phases is by a slowly change of the system parameters that keep you at equilibrium. All right, so with that, let's go and switch to the case of non-equilibrium phase transitions. Let me warn you, however, that the idea of the concept of non-equilibrium phase transition has been used broadly and covered very different characteristics, covering from open and closed systems. And the meaning has a slightly different character depending on what you consider. So for this talk, that is the type of systems that we'll focus, we are going to constrain ourselves to closed systems featuring unitary dynamics. And we are going to explore what is called, in this case, in the setting, dynamical phase transitions. And by that, we are considering the situations where there is a time average order parameter. So it's time dependent, but it's the time average. And this distinguishes two distinct dynamical phases and feature a non-analytic behavior at the critical point. So in some sense, it's very similar to the equilibrium phase transition, but with very important difference. So before explicitly pointing the difference, let me also point out that even in closed systems, there are alternative definitions of dynamical phase transitions. Those have been explored also in very nice experiments, and you can see a very illuminating review of those other phase transitions by Marcus Hale. But in this talk, let's stick with the definition that I postulated here above. And the difference between equilibrium phase transition is that we are talking about dynamical system, dynamical behavior, and therefore the phases cannot be found by minimization of free energy, first. Second, they need to be, there should be dynamical, so in general, they are induced by a quench or abrupt change of fixed system parameters that bring the system out of equilibrium, and more importantly, will depend on the initial conditions. We have new type of symmetries. For example, in these dynamical phase transitions, if I change the sign of the interactions, I might see exactly the different phases. Of course, this is not the case at equilibrium. And moreover, and this is the part that I find exciting, it opens the possibility for the generation of robust entangled state in a different non-equilibrium set. Although the topic or the idea of dynamical phase transition has been explored broadly between theories, actually it's just recently that beautiful experiments are starting to probe this type of behavior. So the first experiment happened in 2018 in JQI by Chris Monroe's group, using a rise of 53 ions where they see a DPT, dynamical phase transition. But the systems that I want to talk today about are actually genuine many-body systems. I want to extend to the case when we are dealing with really several thousands to million particles. And I'm going to describe three different experiments. One experiment that was done at the University of Toronto using fermionic particles. The other experiment done at JILA using cavity system. And another recent experiment done at Hanover using rubidium particles. So with that, I'm going to start by acknowledging the collaborators that made this type of research possible. So of course, my theory group, and I try to highlight the names of the people that contributed to most of the curves that I'm going to present today on all the analytic work that I will to show. Now, the first experiment in Toronto is led by Joseph Taiwansen and his group of grad students and postdocs who have collaborated very nicely. The cavity experiment has been led by James Thompson, and I also highlighting here the postdocs and grad students that took all the measurements that I'm reporting. And the last part is in collaboration with Jan Arl and Karsten Klemp here in Hanover, where we are going to work with rubidium atoms. And of course, Jun Ye has always been there for illuminating discussions. All right, so with that, let me start discussing the different experiments. And while I will start with the Toronto experiment that use a 3D trap gases of fermionic atoms. In this case, we use potassium atom at temperatures about, in a quantum degenerate regime, T over TF between 0.3, 0.5, and we are using arrays around of about 10 to the 4 atoms. Okay, so we're going to encode and spin 1/2 degree of freedom, and this is done in the lowest hyperfine state of potassium, which are very stable. And in the experiment, they use proximilan coils and wires to apply a strong RF pulses that we are doing that we use to implement the spin rotations and actually to control different magnetic gradients. Okay, so the other knob that we have in this experiment that was very important is the capability to control interactions. And this is done by the so-called Feshbach resonance. That is, you can understand basically the Feshbach resonance, the capability to tune the single parameter that controls S-wave collisions at ultra-cold temperatures, that is called the scattering length, when you tune the magnetic field. So this is a plot of the scattering length versus magnetic field. And you can see that by specific values of the magnetic field, that is, you can see that the scattering length can be made very, very large, almost divergent. And this is the case when we are probing very strong interacting atoms. So these are going to be my aggressive hockey players. And this regime has been explored deeply because these offer very interesting capabilities. I mean, in this case, we can explore the regime where we expect hydrodynamic behavior, universal properties, and moreover, connection to high temperature superconductivity and even quark gluon plasmas and perfect viscosity has been explored in this link. But that's not the part that I'm going to talk about today. I'm going to go to the very weakly interacting limit. You see, very close to the zero crossing of the scattering length. So I will have a team of very relaxed hockey players that they barely interact. And initially, you might imagine that this regime is very trivial. I mean, it's almost not interacting. But actually, there are surprises. And hints of this surprise were pointed out back in 2008 by the John Thomas group, where they showed that even in this regime, they were seeing very interesting physics. All right. So the experiment operates, or the measurement of the order parameter in our systems, that is going to be the time average magnetization, is done via what is called Ramsey spectroscopy. The concept, the idea is that I start with a full polarized gas with all atoms in the spin down. Then I apply an RF pulse that creates coherences between spin down and up. I mean, sorry, this is this. So this creates a coherent superposition between spin up and out, and then I allow the system to freely evolve for some time. And in this case, if I look at non-interacting atoms, what happens is that these non-interacting atoms, the Bloch vector that is in the Bloch sphere is going to precess in the XY plane. So I'm going to measure this precession of the phase that is accumulated by the atoms as they are rotating in this free evolution. And this is done by applying another pulse, another pi pulse that transfers coherence into populations. And then I measure the population of the two different states via an Stern-Gerlach technique. So by this protocol, what I'm able to directly observe as this after this measurement of population actually is the total transverse magnetization of the gas. So now I'm looking at collective observables. So I'm look at this collective observable S is the sum over these individual spins over all the sample. And what I measure is the length of the vector in the transverse plane. That is Sx squared plus Sy squared. That is the amplitude of the oscillations that I'm going to measure here. Notice, however, that here we are creating a 50-50 superposition between spins up and down, and therefore the total SC of the gas is 0, and the dynamics is going to be such that total SC is going to remain constant during the dynamical evolution. So because this is 0, then, and we are measuring this quantity, actually I'm indirectly accessing the total magnetization of the gas. And this is going to be used as my order parameter. All right, so now let's try to understand what is the physics that I want to see. Let's start for the simple case when I have a gas of non-interacting atoms. As I mentioned, I have the atoms trapped in a 3D harmonic oscillator where atoms at very cold temperature are going to stack into these non-interacting harmonic oscillator levels. The key point, and what is going to make the dynamics non-trivial, is that the magnetic moment of a spin up and down is slightly different, and therefore these atoms experience a slightly different harmonic confinement, depending if they are up or down. So there is a small difference between the tapering frequencies characterized by delta omega. So now, if we are going to look at the dynamics of these systems, first, because they are non-interacting and the harmonic oscillator levels are good quantum numbers, then during dynamics, the atoms are going to be pinned to these levels, and we can visualize the dynamics as atoms in this energy lattice with atoms formed by these harmonic oscillator modes. And now the point is that because the spin up and down feels a slightly different energy depends on the mode when there are, then the Hamiltonian can be written as just as a bunch of a spin sigma c operators with a parameter, an effective magnetic field that characterize the difference in energy between up and down at the given mode n. Remember, in an harmonic oscillator, the energies are linearly with the mode. So this is the different energies, this is the different phases that are accumulated by the up and down atoms, and just is a simple collection of spin precessing with time. In the experiment, we can change the delta omega by controlling the curvature of the magnetic field, but also because we have a dipole trapping, we can also change that by losing vector light shifts. But I mean, this is just to say that this parameter is tunable. So what is the dynamics? Well, remember, I start with all atoms aligned along the x direction. And then, as a function of time, each atom is going to precess at a different rate. And because they are precessing at a different rate, then they are going to start to dephase. And the collective magnetization is just going to damp at a rate that is set by the variance of my coupling constants Hi. So this is the experimental dynamics of the total magnetization versus time. The dots are experimental points. The solid lines are theory calculations. This is a system with 10 to the 4 particles. And we can see, well, the system just demagnetizes. Another way to understand this demagnetization that I will use to describe the interacting regime is by going to instead of individual spin basis, we can go to the coupled basis of all the atoms. And in this case, the coupled basis is characterized by two quantum numbers, total S and the projection along C. Total S is what characterizes the eigenvalues of the S square operator, and this number S changes from n½ to 0. For n½ the atoms are maximally polarized, and this is where I start the dynamics. I have a full polarized system, but notice that this Hamiltonian, single particle Hamiltonian, doesn't commute with total S square. So then, as a function of time, my system starts to explore different S sectors and depolarizes at a rate that is set by the variance of this coupling constant, of the standard deviation of the coupling constant. So that's the single particle dynamics. Let me now start looking at the case where I go to weakly interacting atoms. So in principle, I have a bunch of atoms moving and interacting at the same time. And in general terms, the dynamics of the system is really hard to solve analytically. However, we are going to take advantage that we can tune the interactions to be extremely weak. So we are going to go very close to the 0-point crossing of the scattering length. And in this regime, the eigenstate of the single particle Hamiltonian remains to be good eigenstates. So in this case, you see that atoms remain in this eigenstate, and the point is that the interactions are weaker than the single particle energy, and therefore interactions cannot make collisions that change the harmonic oscillator eigenmode. This costs too much energy, and therefore these processes are suppressed. And instead, my atoms are going to be pinned in these motional levels of this harmonic oscillator that will act as a lattice sites. So again, we keep the same idea of an energy lattice where the interactions can be introduced, like I can write the interactions just changing the spin. So the interactions, what it's going to do is that going to be flip the spin between the atoms. And these interactions between the spin-spin interactions can be long range. And long range because my atoms are delocalized in these modes. So an atom in harmonic oscillator mode N can interact with an atom in harmonic oscillator N prime because they have some matrix function overlap. So this idea of an spin model of an energy lattice has been, with exhibiting long-range interactions, has been successfully used to describe the dynamics of atomic clocks in Jun's experiment, for example. So here, So we are going to use this spin lattice model without mode changes, and the dynamics is going to be fully described by this spin Hamiltonian that, in addition to the single particle term that I was describing before, I'm going to have an additional term that is parameterized by this spin coupling constants Jij. This coupling constant term is proportional to the scattering length that I tuned by my Feshbach resonance, and also proportional to the mode overlap between these two different atoms in different modes. This is SU2 symmetric, and moreover, you can see a minus sign here, meaning that the full polarized gas is the one that minimizes energy because identical fermions do not interact. Okay, so but this term, this additional Heisenberg term, actually modifies drastically the dynamics, and let me try to explain why. The point of this term introduces a gap in the many-body spectrum that actually favors alignment and prevents the depolarization, the demagnetization of the gas. It energetically suppresses spin flips. And the idea is that if I go back to the sectors of S equal to n-half, where I start and S equal to n-half minus 1, now this term opens a gap that was not present before. This gap can be significantly large because it scales n times the number of atoms times the mean coupling constants. In the case, and this suppresses, if this is large compared to the inhomogeneity of the single particle spin magnetic fields, then can suppress such type of transitions, and the system remains aligned in the decay manifold. In our case, where we have an harmonic trap, this parameter nj bar scales at the scattering length times square root of n. So the key point here is that even though I'm looking at a small scattering lengths, very weakly interacting system where my spin model works, I can make this gap very large by working with large number of atoms. And well, this idea of gap protection has something that I even worked out when I was back doing my postdoc at Harvard many years ago. So we are now exploring this idea very carefully. Another way, so sometimes this is a quantum picture. So people that want to think more a mean field picture, some semi-classical picture, imagine that the Hamiltonian can be described by being mean field Hamiltonian, where my spin I is feeling a magnetic field, an effective magnetic field that has two contributions. The contribution from the single particle term that is proportional to Hi and proportional to the Z along the Z direction. And this is the interaction term that is generated by all other atoms. This is a time-dependent and self-adjust magnetization, total magnetic field that points along the direction of the collective spin. And this is the term that favors alignment. So this idea of alignment in this picture of this mean field picture dates back to the case when people were studying the dynamics of the dynamics of particles into what is called identical spin rotation effect that introduces synchronization of the spins and try to align the atoms. And in fact, this type of synchronization and self-refacing ideas was explored a few years ago in different experiments operating with rubidium atoms. And I'm going to touch back on this experiment later in my talk. So just I want to give a cartoon picture here, trying to explain this self-refacing or identical spin rotation effect. For that, I mean, maybe consider that we have two different types of atoms rotating at a different speed. So if they're not interacting, they start aligned, but because they rotate at a different speed, they demagnetize. However, if you have very large interactions, then they introduces this effective field. They have to rotate around, and this effective field keeps the particles locked. So we have this failed refacing idea that is very interesting. But even more interesting, and this is a point that I find very intriguing, is that if we go back to condensed matter physics, it happens that the Hamiltonian with inhomogeneous transverse axial fields and a collective S.X interaction has been the way that people have described the behavior of BCS superconductors. So this is done through what is called the Anderson spin mapping that maps the two relevant states of the system, a system with no particles as a spin down, and a system with a Cooper pair as a spin up. States with only unpaired electrons are energetically costly, so don't enter in the low energy dynamics. And therefore, the Hamiltonian, if you stare at this Hamiltonian, is telling me this first term is encoding the different kinetic energy between the Cooper pairs and the empty sites. And this is encoding interactions, is written in momentum space, and therefore contact interactions acquire an all-to-all appearance. I mean, they are all-to-all in momentum space, and they emulate our system except by an JC squared term that is a constant of motion. So it's exactly the same Hamiltonian. And for them, the order parameter or gap function is exactly the S minus collective S minus operator. And they note that the absolute value of S minus is just the magnetization that we are measuring in our experiment. The nice part is that this Hamiltonian has been shown to be integrable and belong to some type of Richardson-Gaudin type of models. And our condensed matter faults actually have derived all the methodologies that we need to exactly and analytically solve the dynamics of this nonlinear Hamiltonian. So they use what is called a lax construction, where they have been able to identify an integral of motion. They look at the roots of this integral of motion and then extract a frequency spectrum that rules the many-body dynamics. It's actually quite interesting. And so they are using this type of approach to understand quenches in superconductors when they just change the gap parameter and see the new type of behavior that they have. And this type of proposals, theoretical proposals, looking at quench dynamics of superconductors, have been very active since 2004, where you have seen many papers trying to describe these very different rich phases of superconductors. The point, however, is that in condensed matter systems, it's hard to probe. There was an experiment in 2014 when they were able to do with ultra-fast pulses and probe the small oscillations that satisfy these pseudo-spin mapping. But in these systems, it's not that clear because they need, as I said, ultra-fast pulse, and they are only able to do small quenches. And this is definitely not the case in our atomic system. So what I want to do is trying to now get on intuitions of the dynamical phases that we are going to get by looking at the all-to-all case and first and see what we get. So using the lax construction that condensed matter theories told us, we have this predicted the phase diagram. You can see that there are two different phases that is called phase 1 and phase 2. In the phase 1, the system completely depolarized and corresponds to weak interactions below a critical point, and above these critical points, the magnetization at long time stabilizes and almost saturates at a maximum value for very strong interactions. So we can even get an analytic form of this of the magnetization at long time in this phase 2 gap protected phase. And moreover, we can even compute the gap frequency that is non-zero in the phase 2. This gap frequency introduces transient oscillations that indicate the gap between the two different manifolds in the system. So this is the theory predictions. They agree very well between the numerics and the exact solution, but let me go into the experiment. So this is the phase diagram that we observe in the experiment, where we change the interactions by changing the scattering length, and we can also change the inhomogeneities. We see phase 1, the black region where the magnetization decays, and the stable phase 2 where the magnetization saturates. I can do cuts about different inhomogeneity values, and you can see that a characteristic of the different values is the stabilization of the magnetization at strong interactions and the depolarization of the gas at weak interactions all the time, and a width that increases with increasing inhomogeneity. And I can do also cuts along the vertical axis, and we can, by fixing the interactions, and I can go in wing interacting regime, I can be completely in the unmagnetized phase, or in the strongly interacting regime, I can go into the deep phase 2 regime. Now, if you are curious about the dynamics of the actual system, let's look at this line where we can see in the experiment when we measure the magnetization as a function of time that the magnetization decays in the weakly interacting regime, and I start to increase my scattering length. We can go past through the critical point and start to see a stabilization of the magnetization. You can see also these oscillations that encodes the gap frequency. So if we look at after 100 milliseconds and try to look at the magnetization at that time, and I plotted versus interaction strength, I can distinguish the two phases. For comparison purposes, I can compare with the all-to-all analytic solution. It's slightly different because in the experiment, we do have inhomogeneities, but it's fully accounted by the theory, the red line, when we account for that. Interestingly, the gap frequency is barely modified by inhomogeneities. But the point here is that we do see a clear transition between these two phases. Now, you might be asking yourself, what about if we increase interactions? And that's also the question that we have ourselves, and that's what we did. And when we increase interactions, what we saw is that the magnetization didn't remain stable at a strong interaction, but start to damp, and with increasing interactions. The damping of the interaction is the breakdown of the spin model, and we map this exponential decay of the magnetization by a simple formula that depends on some single particle magnetization that accounts for systematics of the experiment like linear gradients, but also a term that is proportional to the scattering length square that it parameterizes the mode changing collisions. All right, so that's expected, but the key point that you might be asking is, can we test the validity of the spin model? Is really a long-range interacting model that is describing the dynamics? And actually, we verify that by doing a many-body spin echo, where at the middle of the dynamics, we change the parameters of the spin model. So we apply an echo pulse and change the scattering length from A to minus A that reverses the Hamiltonian from H to minus H. And if the dynamics were just characterized by a spin model, we should be able to undo the dynamics. Notice that we are not changing the mass. So if there are other terms, we should not be able to do that. And well, what we see in the experiment is that actually time reversal does work in the weak interacting regime. These are the experimental points that we see that we can do. There is no dynamics in all this region, and instead there is a strong decay of the magnetization at stronger interactions. Okay, so one final comment, because before I talk about thermal bosons, actually thermal bosons behave like fermions because multiple occupied sites are suppressed. And if I operate in the regime where collisions that change modes are suppressed, the collisional regime, I should be able to actually reproduce the spin model dynamics. Actually, this is the collaboration with Jan and Karsten, where we can write an effective spin Hamiltonian for rubidium gases. Now, where spin down and up are two hyperfine states in rubidium, we can write an equivalent spin Hamiltonian. But in this term, because we have bosons, up, up, down, down, collisions are allowed. So in addition to this S.S term that we have for the fermionic system, we have an additional term that is in a CSC Hamiltonian. And this SC Hamiltonian, however, we are lucky enough that if the orbitals of the atoms are behaving similar, like in the case, so that in many situations, then this term happens that because of the conspiracy of the scattering lengths, this term can vanishes, and actually what we recover exactly the same Hamiltonian that we have for fermions, for bosons, and these were prior measurements done in Peter Roshan group, where it shows the demagnetization to preservation of magnetization, even in rubidium systems. This was not understood as a dynamical phase transition, but we can see similar dynamics. So with that, I'm going to finish the part of try to understand the behavior of collisions in cold gases. So it's a good time to stop for questions.
Okay, so we have already several questions that came by email. So the very first one is from Bill Phillips from your introduction, because you talk of boson-mediated interactions for ions and for atoms in a cavity, and he was wondering what about gas of fermions embedded in a gas of bosons? Could you comment on this type of long-range interactions?
Yes, well, in general, that type of long-range interactions are kind of effective interactions. So the underlying principle is similar to this type of interactions. So for example, in the bosons, because the bosons are delocalized in principle because they can mediate very long-range interactions, I think they're not going to be nevertheless all-to-all, like in the case of the cavity system. So I think in the case of RKY interactions, I think it can be like 1/r³, depends on some, but they have some power dependence. So I'm thinking the spirit is more, I would say that these type of interactions are more kind of the long-range spin interactions that I'm getting effectively in the system.
Mm-hmm. So there is another question from Bill Phillips. So he asks, in the Toronto experiment, you characterize the weak interactions as being long-range because the spatial wave function is delocalized, but it is still a contact interaction. So he wanted to know a bit more about this.
Yes, exactly. So the localization is because I'm working in mode space. So like in positional momentum. So the localization is because a particle is in an harmonic oscillator mode n, and this particle in mode n can interact with another particle in n prime because the particle in this mode space are delocalized. So it's like contact interaction in position are all-to-all interactions in momentum space. So basically, this is the characteristic. Yes, it's coming from the localization and pointing back to the first part questions about boson fermion mediatic interactions. I think that they fall into the same category that I'm talking about here.
Mm-hmm. So then we have another related question. So if we have long-range interactions because we have a weak contact interaction and the atoms are delocalized, that's exactly what you said. What does that mean for the timescales in the system?
Yes, that's an excellent question. And the time of the systems, of course, is going to be, I can only prove times where this collisional process that demagnetize, that this term proportional to A squared, that is going to change the modes, are going to start to affect the dynamics. So here we are stopping the dynamics at 100 milliseconds. And if we were able to go longer, I mean, there are other type of demagnetization mechanisms that are faster than this type of mode changing the collisions, because here there are magnetic field fluctuations that unfortunately decohere the gas. But it's true, I mean, our time scales are going to be strictly only shorter than the time that these mode changer or thermalization processes start to kick the gas. There can be much longer than the time scale necessary to look at the validity of the spin model. So I think we can define these two different time scales of the system, collisionless and longer times where collisions matter.
Mm-hmm. And then a follow-up question actually in the same one. So does that set a bound on the maximum size of the system that one can reach?
Well, not necessary, as long as we satisfy, well, I mean, what matters is A times the square root of n. So if I have more atoms, then I can reduce the scattering length more. I mean, that's the nice part of the Feshbach resonance, that I can tune my scattering length, and I can keep my A square root of n actually constant. So you can see that if I go to weaker interactions, then collision is processes that are not accounted in the model are less important. So having large n in principle does help.
So may I ask you something? So in this plot that is now there, it looks symmetric in the theory for the attractive and repulsive interactions, but not in the experiment. So are there different like breaking of the spin model mechanisms for attractive and repulsive interactions?
Well, that is one of the interesting parts here, that for the dynamics, we don't see, well, there is a Feshbach resonance, a P-wave Feshbach resonance sitting, and we think that this faster demagnetization key here could be accounted for that. So this is true. On the other hand, is that actually these spin changing collisions, A squared, are not completely symmetric. That's true. So we don't know which one is the leading reason of why this is a little bit faster than the other process. And so here, for example, when we do the time reversal, we don't see too much asymmetry. So I don't know. This is a good question, and why the source of this asymmetry in the experiment.
Okay, so we have another question in the chat from Vincent Liu. So from the spin model, it seems that the spin exchange is over all sides. Is the theoretical calculation obtained for 1D?
The theoretical calculations are obtained for 3D. This is easy to do because we are doing a mean field theory, and in a mean field theory, looking at 10 to the 4 equations, or it's not impossible. I mean, we do a scaling analysis, so we can, for example, simulate 1,000 particles, and we do a scaling analysis that allow us to actually scale to the parameter, to the 4 particles that we do in experiment. Yes, but the theory is done in 3D. Only the only curve that I showed that is 1D is the analytic solution. This is harder to get in 1D. I mean, we have some fitting parameters to convert the 1D solution into a 3D solution.
And then a very last question before we go on. In a harmonic trap, the interaction strength should decrease slowly with the difference in harmonic oscillator quantum number n. If you use this way to create very long-range interactions, to what extent it is important in the resulting dynamics that this is not exactly an all-to-all interaction?
Perfect. This is a very nice question. I mean, the fact that we see, that's what we call inhomogeneities. When we talk about the inhomogeneities is the fact that we are not have S.S, collective S.S, but the fact that the interaction actually changed with harmonic oscillator mode slightly. So actually the harmonic trap gives a dependence of the mean interaction proportional to 1 over the square root of n. So this introduces some modification of the, and you can see that the mean coupling constant is actually weaker than what we can compute a coupling constant that depends on n. But so you see that it can introduce modifications in the quantitative behavior of the phase transition, but not necessarily in the qualitative behavior.
Okay. So let's go on for the sake of time, and let's take more questions at the end.
Okay, so in the last couple minutes that I have, let me go back and look at the baseball players and start looking at cavity-mediated interactions. In this case, the experiment that we did was in collaboration with James Thompson group at JILA. Here, we trap strontium-87 atoms, that is a boson, in a cavity. Actually, we operating in a new regime of cavity QED in the sense that we use the 1s0 and the 3p1 state as the effective spin states. You can see that we are doing an optical transition and the excited state is directly involved in the dynamics. This is different for typical cavity QED experiments where the up and the down state are grounds, the hyperfine ground states, and then we use, in that case, they use Raman transition. Here, the cavity is directly coupling the two transitions, and we have a cavity in the tuning delta between these two. Of course, there is cavity losses parameterized by some parameter kappa. The lifetime of the 3p1 transition is what allows us to use this optical state because the lifetime actually is of the order of 7.5 of the decay is 7.5 kilohertz. That is much shorter than any of dipole allowed transition, and therefore allows us to actually use this state as an active state. We operate in the regime where the detuning is very large compared to other parameters of the system, much larger than the cavity detuning, and the dynamics in this regime becomes unitarity. The role of the photons is just to virtual mediate interaction between the atoms. Basically, if I have an atom in the excited state, it can emit a photon. Virtually, this photon is absorbed by another atom, and as a result, I will have a flip-flop process. This flip-flop process is in the form of J plus J minus, with a coupling constant chi that is proportional to G squared, the single particle Rabi frequency divided by the detuning. So here J are my collective spin operators that introduces the flip-flop dynamics. I noticed that, well, there is also dissipative processes that are set by kappa, that is the super radiance emission, but because we are in a parameter regime where delta is much larger than kappa, these processes are really suppressed and we don't have to worry about them. So what we do is actually we drive the cavity with a coherent drive that is detuned by that atomic transition by delta, and this introduces Rabi flopping as a frequency omega. So the spin model that we write is this collective model when you have J plus J minus and this transfer and longitudinal fields, and this model is called the Lipkin-Meshkov-Glick model, that is known to feature an iconic dynamical phase transition where the order parameter is the time average magnetization, JC. So if we plot the phase diagram of this system, we can see as a function of the normalized detuning and the normalized Rabi drive, there are two different types of behaviors what we call the ferromagnetic behavior. Here we are starting with atoms all pointing down, and the ferromagnetic behavior is where the interactions trap the atoms in the south pole, and the system just does small excursions around the south pole. And in the paramagnetic region, interactions are not important, and we see mostly dynamics dominated by Rabi flopping, and therefore the dynamics is very sensitive to variation in omega and delta. So we try to explore this phase diagram in the experiment. Actually, what we did is trying to look at the different lines of the phase diagram. The first point is when we set that the tuning close to zero, the axial detuning, and we are going to transfer this line, and we see that for strong interactions, weak drive, the system gets trapped in the south pole. Where I am going to increase to 0.2, still in the ferromagnetic region, we see that the excursions are a bit larger, but still limited to the south pole. And I go to the paramagnetic region, where I start to have large amplitude oscillations. The systems go above the equator. And here deep in the paramagnetic phase, for a strong gravity drive, we have just single particle motion that is here in the cavity is slightly damp because we have some inhomogeneities in the cavity couplings. However, when we account for these inhomogeneities, the theory reproduces very well the phase diagram. Moreover, we also care about the scaling with particle number, and we see that we can change the particle number by 3 times, from almost a million particles to a few 10 to the 5 particles, and we can see that all the lines collapse. And actually, this is a plot taken, a measurement taken at 4 microseconds. And we can see that we explore the change between ferromagnetic to paramagnetic behavior that is scaled with n, and everything collapses when we do the proper scaling and agree with the theoretical calculations of the expected phase transition. We can also explore lines along the horizontal direction. So these are cuts along this direction where we keep the Rabi drive fixed and we change the detuning. And we can explore this region when interactions are strong. And we can see that in contrast to the single particle characteristic Rabi line shape, we see this very abrupt transition from a ferromagnetic where the system is almost keeping down in the south pole to a paramagnetic phase where we manage to excite the system. And moreover, the new symmetries of the dynamical phase transitions can be clearly seen by the fact that we change the magnitude of the detuning, that change the sign of the interaction. We recover the same phase diagram just reflected. We can go this, or we can explore the a little bit more strong interactions where we see a broader line. Actually the sharpness of the transition is less abrupt, but we can see very similar features that we have between we have the paramagnetic phase where we excite and the ferromagnetic phase. So in some degree, we have been able to characterize the phase diagram in this cavity system and show collective behavior. So something that I want to finish this talk in the 5 minutes that I have left is actually mention, again, emphasize the synergy between these short and long range interactions by showing you that we can implement similar type of dynamical phase transitions that we saw in the cavity in an ultra-cold system. So go back to rubidium gases, where we use the spin down and the spin up as due to different hyperfine states in rubidium. As I mentioned before, if we have a similar way orbital, so the two states feel almost the same trap, then we have the issue that this term, that is the C² Hamiltonian, disappears because of the conspiracy in the scattering lengths. So we recover the Hamiltonian that we had with Joseph. But what we wanted to do is to come up with a way that we can turn this parameter and make it different from zero. And a natural way, of course, is to make the orbitals slightly different, because then if they are different, you can see that this doesn't average out in the interaction parameter, and we are going to get a non-zero chi behavior. So how we do this? Well, the simplest way that we came up, this is in collaboration with Karsten and Jan, is by actually not exciting a carrier transition, but trying to excite a blue sideband transition. For example, I'm going to do here. And in this case, this is excited to Raman transition, but the important part is that if I go back to my spin model, now my spin up at psi I is going to have different orbital component than my spin down at sign I, because the down has quantum number Ni, but the app has quantum number Ni plus 1. This is for the blue side transition. So I'm going to have different harmonic oscillator orbitals, and therefore I can set on this chi term and make it to be non-different from 0. And again, this is exactly the same Hamiltonian that we have in the cavity. And if I look at the predictions, I'm just rewriting the phase diagram that I have before. We have a ferromagnetic case when interactions dominate, chi dominates, and we have a paramagnetic phase with the single particle dominates. These are oscillations along the very close to the South Pole, and these are large amplitude oscillations that are in all the set by omega and delta. Okay, so now let's look what the experiment saw. And actually, this is the phase diagram that we draw for the parameters of the experiment. This is, they have also inhomogeneous couplings slightly because of the trap, but we normalize by the inhomogeneity. And this is the phase diagram that we expected, very similar to the one I showed you in the cavity. And these are different measurements of the average number of particles in the spin up that is parameterized by JC, similar to before, as a function of the detuning. And we can see a transition from a ferromagnetic phase where the system remains trapped down to a very sharp behavior and abrupt change to the paramagnetic phase, and then go back to the paramagnetic phase. And we can delineate very well the phase boundary by changing the density of the particles from very low density to larger density as a function keeping same time that is in the dynamics. So here is just a comparison with the all-to-all model that is slightly modified, but very similar to the inhomogeneous case. So here, hopefully I can emphasize that we have very similar behavior. And with that, I want to finish my talk, hopefully showing that I can told you a little bit about dynamical phase transition, the new symmetry that emerged, and just mention that one part that I have not shown you, and that's the most exciting part perhaps, is the ability to actually generate robust entangled states. So far, everything has been at the mean field level, but one of the promising directions is that if we can explore longer times, we might see the emergence of beyond mean field features, and this is in progress, and we're trying to see this in the 3D optical lattice clock at JILA that features a quantum degenerate gas with all the levels at the quantum level. Is a 3D lattice clock with 10 to the 4 atoms, very cold temperature, and we hope soon that we can see beyond mean field signature there. The coherence time is longer than 12 seconds, so we hope we have chances to do that. And with that, let me finish the talk mention that I think there is a bright future ahead, and hopefully there are many things to explore in ultra-cold systems. And thank you for your attention.
Thank you very much, Ana Maria, for the great talk. So we don't have so much time left for questions because we had many questions in the middle, but we still have a few of them. So there is one by email from Yuting Chen that would like to know the connection between the all-to-all spin models that you were discussing and the other models like the Hopfield model. Maybe you can comment on that?
The all-to-all models and the connection with what other model?
Hopfield model.
Hopkins? Yeah, the Lipkin model?
The Hopfield model.
Hopfield model. What is the Hopfield model? These are particles that are leaflets that are localized, and then they are mediated by long-range interactions. Yes, I mean, everything that is long-range, in principle, will map into our systems. I mean, I think in the Hopfield, you have different impurities. In principle, this could be implemented in qual-atoms experiments too. For example, you have 2 bands in the lattice where the particles in the lowest band become localized and the particles in the first band become model. So I think they're related, not implemented here, but could be explored in experiments for sure.
So then there is another question from Gal Ness. So he has a question concerning the Toronto experiment, because he says there is a first intermediate pi pulse that was done to offer a first order correction to the dephasing, and he would like to know what would happen from higher order techniques of dynamical decoupling like the ones used in NMR experiments.
Perfect. Yes, of course, this will help in principle to maybe reduce some of the dephasing that we are seeing. We are not, I mean, At the moment, the pi pulses in this case not always helps. I mean, that's something that we discovered that I think that a pi pulse always refaces your atoms. Actually, there has been experiments also showing that because the S.S Hamiltonian doesn't commute with Hi sigma Ci, then in this case, not only a single pi pulse helps, but I imagine that you apply dynamical decoupling at many times, you are able to always reface your system as much as you want. So definitely, this is something that could be done. We didn't have the need to do that, but it could be useful.
I actually have a question concerning the Hanover experiment. So you showed the trick that they used to make the orbitals of the two spin states different. Is different in this case versus just doing it with different scattering lengths. Instead of rubidium, they had another atom that would allow to tune the interaction term.
Perfect. That would be perfect. Yes. Anything that if you have a bosonic particle that not rubidium, but you have something that this difference A up plus A down minus 2A up down is different, then you are going to implement the C square Hamiltonian immediately. So yes, it's just a conspiracy for rubidium that actually these parameters magically cancel. But as long as you have different parameters here, then you will get an C square Hamiltonian.
So we have still a couple of questions. So another one from Bill Phillips by email. So he says, thinking about the Toronto experiment and the phase transition between retaining magnetization and having it decay, the picture was of an effective field about which dephasing spins would precess, retaining their magnetization. So he would like to know, is there a way to understand that these or other interactions lead to a phase transition as opposed to a crossover?
Yeah, this is an excellent question, Bill. I necessarily don't know the answer. So, for example, I can tell you in our case, there is a transition, for example, let's go to the Lipkin model. You see two regimes, like in the water diagram, sometimes you have a phase transition, some have a crossover. In our experiment in the Lipkin model, you can see that there are two regimes in the phase diagram. Here. Here, you can see that this is this sharp line that distinguishes a ferro and a paramagnetic phase. But at some point, when you are weak, when interactions are weaker, then you cross the sharp line because a simple crossover. So the line of phase transition disappears here. So I imagine that in general, if you have two competing phases of non-commuting operator, maybe you always have a phase transition. It can be quite complex. So in this case, the phase transition is very simple because the Hamiltonian is simple. So I don't know how complicated order parameter you need if you have more complex model. But it is true that not all the times you have an abrupt change, but some regime you can have just a smooth crossover. So I think this is an excellent question, and I think this is something that we are investigating.
And then let's take the very last question. So you talked at the end about promising schemes for robust generation of entangled states. So could you say a bit more about that? So for a lattice clock, how would you set this up? And then individual lattice, or which harmonic traps you would like, and so on. Huh?
Yes. So interestingly, we have already shown that in the hover model, similar behavior happens. So in the hover model, if you can make, and this is something that we can do in the clock via spin orbit coupling, the spin up and the spin down atoms feel a slightly different dispersion. This actually emulates the inhomogeneity that we see in the trap. So what happens is that you are in the gap protected phase here. In principle, you have very stable dynamics, but this inhomogeneous to higher order generates an effective SC square Hamiltonian. So to first order, if you project the inhomogeneities in the gap manifold, is just average sigma C. To second order, when you project the inhomogeneities, they have to be small, so you are going to be in the stable phase. You generate an SC square Hamiltonian, which is iconic for spin squeezing. So the hope is that if you are here in the stable phase, and you are really stable, very long time, you should be able to see spin squeezing started to happen in the gap protected phase. So we have a paper on that. So that where we explicitly discuss how is the protocol that we envision to do in the clock in order to generate the spin squeezing.
And then a question actually, which was a follow-up of the same question. So are these long lived enough states on the scale of the normal interaction time for lattice clocks?
Yes, so in principle, I mean, they have now time scales that goes up to 12 seconds. We think that we can generate the spin squeezing at time scale smaller than 1 second. So, of course, it's going to be a trade-off because the spin squeeze state is going to be more fragile, and you're going to always have, I mean, current clocks have a fantastic sensitivity and precision. So up to an extent, you can beat this very long time interrogation by some kind, the squeeze state that we create is going to be stable enough. It is going to be seen. But in principle, the theory predicts that you could generate an spin squeeze state at 1 second, and in principle enjoy and generate up to 15 dB of squeezing in the clock. That might help the precision. So that's the theory prediction. The experiment will tell us if we are correct or not.
Okay, so thank you very much, Ana Maria. So maybe there are still a few questions that we did not answer, but for the sake of time, I think we have to stop here. And if you have even more questions, you're most welcome to send them by email, because Ana Maria proposed to answer them in written form. So with that, besides thanking you very much, I would like to give the word to Sebastian again, that will make the last announcements.
Yeah, thank you, Letizia. And thank you, Ana Maria, for a great talk. And please also note, I would like to close out that Ana Maria's talk was the last talk before our summer break. We are going on holidays in August, and we will be back in September. So the talks are going to start back up in the beginning of September. And if you want to know precisely what's going to happen, please go to our website, quantumscienceseminar.com, subscribe to our email list that's linked there, subscribe to our Google Calendar, follow us on Twitter. And you should certainly check out our sister seminar, the AMO seminar, where tomorrow Selim Joachim will actually talk about a very different approach of studying quantum many-body physics, where he uses single fermionic atoms to learn something about many-body physics. And with this, I'd like to thank you for your interest and hope to see you again, not next week, but in September. Same time, same place. Bye.
Thank you.